I'm going to talk about some old material, but for which, after almost 30 years, uh, there are a lot of questions without answers. So this is the superconducting phase diagram of cuprates. So this is the plan of my talk. After an introduction, I'll concentrate us on some features of the phase diagram. Then I'll talk about these copper oxide planes, which are central, especially for the mechanism of doping. Then I'll describe the model I use, derive the gap and doping equations, and then I'll be able to get an expression for Tc as a function of doping. And then I'll show the results for these different materials, and then I'll talk about multi-layered cuprates. So these are my collaborators. Reginaldo is a PhD student. Eduardo is a former postdoc, and Van Sérgio is a professor at Belém, Pará. So superconductivity, as you know, was discovered in 1911 after Camerlin Owens mastered the process of helium liquefaction. A landmark in superconductivity was the Landau-Ginzburg theory, 1950. And it was in 1957 that the theory, final theory for superconductivity was put forward by Bardeen, Cooper, and Schrift. So you see, there are about 45 years between the discovery of superconductivity and its understanding. But it's important to remark that meanwhile, in the meantime, the whole quantum mechanics was developed, because in 1911 we didn't have quantum mechanics. So in 1986, as you know, Bednorz and Miller discovered a new type of superconductivity for the first time, going beyond the 30 Kelvin mark. And so far, almost 30 years after, we still don't have a satisfactory theory for high TC superconductivity. So a central issue in the physics of the cuprates is the phase diagram, the famous phase diagram, which has the main features are this antiferromagnetic dome, the superconducting dome, and this pseudo gap. So I'm going to focus on three basic features of this phase diagram, which so far have not been properly described by any theory. So what are these three issues? First one is the superconducting dome itself. We have experimental data, but there is no theory providing analytic expressions for the critical temperature as a function of doping. So here we have LSCO, the mercury 1201, and the bismuth material. So the second feature of the phase diagram, which we are going to concentrate, is the dependence of Tc on the number of layers. But as we know, these copper oxide planes are central in the physics of the cuprates. But there are materials with 1, 2, 3, 4, 5, and so on planes. These are basically the copper oxide planes. And there is an increase of the temperature as we increase the, it's a complex behavior. As we increase the number of planes, the temperature first increases. You see, here's the bismuth family. We start with 34 for one layer, 92 Kelvin for two layers, and 108 Kelvin. This is the maximum, optimal temperature. So, from the theoretical point of view, there is nothing about this. No explanation. Take the mercury family, for example. We start with 97 Kelvin, 125, 134. And if you increase, these temperatures go down a little bit, and suggestive becomes similar to the two-layer. So again, no theoretical explanation for this. This is representation of the optimal temperature as a function of the number of layers. So you see, for example, this is the mercury compound. It increases, this is N1, 2, 3, and then it goes down and stabilizes. And for some materials, it even goes down. So we don't find any explanation for this in the literature. So we are going to provide an explanation for that. And the third feature of the phase diagram, which I'm going to concentrate, is the fact that as, again in multi-layered cuprates, as we increase the number of layers, the superconducting dome becomes closer and closer to the antiferromagnetic dome, and eventually superimposed to it. Again, so far, no explanation for that. So we are going to provide a simple explanation for this. As you will see, I'm not going to do anything fancy here. I'm going to do something very simple. So, a central property of all cuprates is the presence of these copper oxide planes, which have some peculiar features. So we have copper ions on the sides of this square lattice. This is this is copper plus plus in a 3d9. So these are d orbitals, and the oxygens are on the links of this square lattice. We have px and py and px orbitals, which are coplanar with these copper oxide planes. But, okay, so the copper lattice is half-filled, but it's a Mott-Hubbard insulator. So these are localized spins which interact via a super-exchange coupling, giving an antiferromagnetic insulator state. Now, from the point of, this is well known, but from the point of view of the oxygen lattice, an attentive analysis shows the following. If you take, for example, the px orbital and the py orbital in the nearest neighbor, they are bridged by overlapping with the copper orbital, whereas the py here and the px here are not. So this makes the oxygen lattice very peculiar in the sense that there are two sublattices, one with px orbitals and other with py orbitals, which are really the active ones. Because, for example, as we dope the system, we create holes in these orbitals, and they will hop. The hopping will be assisted by this overlap with the copper orbitals. So this gives us two. This is a representation of the oxygen lattice. So we have two sublattices with px and py orbitals, which are bridged by this d copper orbitals. So if we take one side of this oxygen lattice, we have, for example, this, say, px orbital. It has 4 nearest neighbors, which are py orbitals, connected by these vectors here. Okay, so this is going to be. So the mechanism of doping, we introduce, as we dope the system, we introduce holes in the oxygen lattice. And at the same time, these holes create skirmions, defects in the copper lattice. This is an old idea advanced by Pasha Wigman, Schreim, and many people, which we explored in these papers with Marcelo Silva Neto. We are able, using this idea, we were able, for example, to describe the antiferromagnetic dome of LSCO. Okay. So if we consider the oxygen lattice, which has these two px and py sublattices, let's call the number of electrons and the number of holes. We have the number of electrons is 2, because the parent compounds are fully filled. They are a band insulator because they have 2 electrons per side. And the number of, if we call the number of holes 2y, where y is between 0 and 1, we can write the number of electrons like that and the number of holes like that, where y equals 0 means the pure system. Now, the problem is how to express this y in terms of the stoichiometric x parameter, doping parameter. This is not a trivial issue. And in general, y is a function of x, which varies according to the compound. We don't have the same function for all cuprates. So in order to avoid this, we are going to formulate our model in terms of x and not of y, because that's the thing which we have control. So the model is the following. So we have this Hamiltonian. Psi are electron hole creation operators with spin sigma in sublattice A, B of the oxygen. So the first term is just a hopping parameter, hopping term with a hopping parameter t, where a hole hops from the A sublattice to the B sublattice, where the B sublattice we sum over the 4 vectors connecting the nearest neighbors. So this is the kinematical part. And then we have the dynamical part, which is a BCS-like theory. You see, phi you can take as a Hubbard-Stratonovich field. If you integrate over phi, we get a quartic BCS-like interaction. But it's a peculiar one because the superconducting order parameter is the expectation value of phi. And it will involve Cooper pairs belonging to these different oxygen sublattices. This is inspired in a result we got in this paper from the spin fermion model. So there's another issue here. If you look attentively to this oxygen sublattice, we see that we have signs in these px and py orbitals. And if you look at this overlap here, there is a minus net sign on the vertical links and a plus sign on the horizontal links. This yields this property here, which we are going to show is responsible for the D-wave character of the superconducting parameter. So in momentum space, we just do the Fourier transform, we get something like this. This is the usual hopping term, where epsilon is the tight binding energy. And the superconducting order parameter, as I said, is given by this vacuum expectation value. So this is the Cooper pair expectation value. And you see it involves holes belonging to different oxygen sublattices. And delta of K is this Fourier transform here. And if we use this property, it's easy to show that delta of K has D-wave character, as the phenomenology indicates. So, okay, if you look at the eigenvalues of that Hamiltonian, mean field eigenvalues in which we replace the Cooper pair, the Hubbard-Stratonovich field by its mean value, we obtain these eigenvalues here. And if we expand these so these eigenvalues vanish at these 4 points here of the first Bill-1 zone. And if we expand these eigenvalues around these 4 points, we obtain the curves of constant energy are ellipses with semi-axis proportional to the energy. So this is the shape of this. So each of these is a constant energy surface or curve. So if we compare with Harper's results, we see that this is in excellent agreement with what you see experimentally. Here again. These 4 points here are the points where the energy eigenvalues vanish. So we are in good agreement with experiments. So now we assemble the whole creation operators in this Nambu fermion field. The sublattices A and B, spin up, spin down. And A, we represent here, A is a number. I'm allowing for many layers. And I call A just a flavor-like number, specifying to each layer these holes belong. So it goes 1 to n. And in this approach, we are not going to consider interaction between these layers. So as a first approach, we will consider these layers as no interaction. So this is the Hamiltonian. And then we are going to introduce doping by a constraint on the fermion field through a Lagrange multiplier, which in a functional integral representation are going to integrate over lambda. So we introduce, and delta we're going to see is some function of the stoichiometric doping parameter, which we are going to specify. Yeah. Yeah, okay. It's a very good point. I'm going to show that it matters because when you have many layers, they are not going to be doped uniformly. So I'll come back to this point. And delta of 0 must be true because without doping, we have 2 electrons per site. And so without doping, this is basically the electron density. And we must have this. So we construct out of the Hamiltonian an effective action and integrate over the fermion field, which is quadratic. So we obtain this. This is already there in the Hamiltonian. This comes from the constraint, and this comes from the fermion integration. This K0 is to transform the Hamiltonian into Lagrangian because we want to have an action. And lambda is the Lagrange multiplier field. So by doing that, we obtain an effective action. It's a function of delta and lambda. And we just minimize. We take these 2 conditions. We will produce 2 equations. One, this will produce what I call the gap equation, and this will produce what I call the doping equation, which I call delta and lambda satisfying these conditions at delta 0 and lambda 0. So in order to obtain this, and in order to obtain Tc of x, I impose delta is equal to 0, because delta is equal to 0 is the threshold condition for the superconducting phase. And the doping equation gives this relation between the chemical potential and that delta function. Observe here I have a certain lambda, which is an energy cut off, and a certain alpha, which is expressed in terms of a characteristic velocity. I'm going to specify soon. So, sure. Yes. Well, it will influence through this velocity will depend on the hopping parameter. Well, I'm going to determine what is delta of x. And then, of course, you can do a small x expansion. So the gap equation gives this, and when I impose delta equal to 0, I'm having Tc of x. So this is equal to C. Now this lambda 0 is given by this. I'll show you what is eta and what is Gc. So this, from this, I immediately obtain that equation where This lambda 0 is given in terms of this eta and GC. GC is alpha over lambda, and eta is this function here. And G is the coupling parameter of my model. Now, if you look attentively at this equation, you'll see that the temperature, critical temperature, will be maximal when the chemical potential vanishes, because for lambda equals to 0, hyperbolic cosine is 1 and logarithm of 1 is 0. So we have first this T max, which appear here, is expressed in this way in terms of the function eta. And from this equation, which I repeat here, I conclude that the chemical potential at the optimal doping must vanish, which implies this function has a maximum at T max, given by that expression. So this is the... So lambda 0 of optimal doping must be 0. I repeat here the expression of lambda 0. This was the condition I had with my delta of 0. So for satisfying this, I must have delta of x0 equals to 0. So I can satisfy these two conditions with a simple parameterization given by that. There's something wrong here. So if I combine these two, I obtain lambda 0 is 2. This is, we must read it from here, from right to left. I don't know why. One of the mysteries of the PowerPoint. So you see that this satisfies, the simplest parameter is satisfying this. And this, so the lambda and the alpha, so that alpha is expressed in terms of this characteristic velocity, which is written in terms of the hopping parameter and the lattice parameter. That's how the lattice comes. Well, I'm introducing the holes through this constraint, but the lattice is just the square lattice. And this energy cutoff, I relate it to the coherence length, which in the cuprates is of the order of the minimum coherence length of the order of 10 angstrom, whereas in conventional superconductors is of the order of 500 angstrom. So this is, so lambda is the energy, characteristic energy corresponding to this coherence length. Okay, so we are ready to show our results. So we take these superconducting domes of different materials. These are experimental results. So we start with LSCO. We adjust just one parameter, which is this gamma. We are going to compare first our results for single layer, so this n is equal to 1. So GC, remember GC is given completely in terms of lambda and alpha. So the only thing I'm going to adjust is this gamma. which is basically G, because GC is fixed. A is the area, X0 is the maximal doping, optimal doping, and this eta is given by this. So adjusting gamma is basically adjusting G, the coupling. That's the only adjustment we do. So this is our theoretical curve for LSCO. X0, we enter with the values of X0 and T maximal and adjust just the interaction coupling. See that the only expression, the only attempt to describe this TC of X was made almost 30 years ago by a parabolic fit of that expression for LSCO. Here. And I reproduce here the parabolic fit and superimpose with our result obtained from that model. Our result is this solid curve, and the parabolic fit is the dotted line. Excuse me? I leave up to you to judge. This is TC as a function of X. TC. What? Which gap? The superconducting gap? Okay, I'm not plotting it here. LSCO. Lantern, Strontium, copper. Well, the experimental points are these. You can see here, for example. The data are from these people here, experimental data from these people. So now let's go to mercury and bismuth, for which there was even no parabolic fit. Yes? Excuse me, could you repeat? Yeah. Yeah. That's correct. You mean this? This? Well, I'm going to determine this as a function of, I'm going to determine these 2 points here. Yeah. I'm just introducing this expression. That's how. And I enter the value of. Okay, we can return to this point. Let me go to bismuth and mercury. So bismuth and mercury are asymmetric curves, as you see. The only symmetric curve is LSCO. So I take our expression. This can be rewritten like that. We just expand the hyperbolic cosine. And in the case of LSCO, we have this moduli here, which convey the fact that it's symmetric. But in the case of bismuth and mercury, we have different expressions on the left and on the right. The reason is when you expand this function here, if x is greater than 0. In this case, we can expand this when x is negative. When x is positive, I can't. So I have to do different expansions on the left and on the right. This is the origin of the two expressions here. And then I plot, again, adjusting just this gamma parameter and entering with x0 and t maximum. This is comparison with the experimental data for bismuth, single-layered bismuth. This is the same expression on a scale of 300 Kelvin. It's exactly the same, just the scale is different. So you see, it's quite good. By doing different expansions of that function, well, if I keep this moduli here, it's symmetric, but I just remove the moduli. Yeah. Well, because experimentally it's not symmetric. Yeah. Okay. Yeah, I'm not looking at the gap at the gap expression as a function of temperature. Yes, yes, yeah. Because you can see here. I have this expression here, a lambda 0 is given by this. So and lambda 0 is given. So actually, the solution comes without the modulus. For LSCO, I impose the modulus, just to account for the fact that it's symmetric. But yeah. Yeah, that's correct. That's correct. Yeah. Yeah. It's not a fitting parameter. It's because I don't have choice. I must use that one. It's like in QED. Everything is a function of the electron charge and mass, but I must enter the experimental values. But I don't have choice to adjust it. So it's not a fitting parameter. Just G is adjusted. Just G is adjusted. So this is for mercury. And this is on a scale of 100 Kelvin, and here on a scale of 300 Kelvin. so it's quite good. Okay, so here I'll determine the two quantum critical points, which are this and this. So for this, we just take the original equation and take Tc goes to 0. So if we impose Tc goes to 0 in the equation for Tc, I get these two values here. So this is S minus, this is S plus, are given by these expressions here. So I come to multi-layered cuprates. First, let me remark that the optimal temperature is given by this expression, where eta is given by this. So you see that the only thing that n does is to enhance the coupling. This is like when you do 1/n expansions, you know that. So the presence of n layers makes G goes into Ng. And so if we assume that the couplings G and Gc are the same for all members of the family, then the ratio of T optimal for n layers with respect to T maximum with one layer is just this. Because if I assume that everything else is exactly the same, and even G and Gc for one family. So if I do that, I have the T maximum for n. This is for the bismuth family. So this is n equals to 1. So for n equals to 2, we see we have excellent agreement. For n equals to 3, it's not so good. This on the right are just the result of this equation here. So now let's come to the mercury family. So for n equals to 2, we hit right on the temperature. For n equals to 3 is also very good. This is, I think there is a 1 lacking here. It's 134. So for n equals to 4, now it's not good. And for n equals to 5, again. So I come to your point. So it's easy to understand why this is so. Because if you look at the structure of these layers, this is mercury with n equals to 2, 3, and 4. So these are the 2 layers, 3 layers, 4 layers, 5 layers. Now, what happens is that the charge reservoirs that we create by doping remain just these 2 charge reservoirs. While we introduce, this is just one plane, so this plane is adjacent to the charge reservoir, so it is easily doped. For 2, again, these copper oxide planes are adjacent to the charge reservoir. Now, for n equals 3, it starts to become a little bit difficult. You see that's why it starts to show a discrepancy. And if you go to n4 and 5, then it's complete because you just don't dope these inner planes. But we still dope 2 of them. That's why the results of n equal 4 and 5 are basically the same as n equal 2. Absolutely, absolutely. The inner planes are still antiferromagnetic, while the outer planes become superconducting. That's why there is coexistence of superconductivity and anti. Exactly. By the way, this is the next effect. So, okay, I'll show here. Okay, here. So this is the mapping of the dopes. N equals 1, 2, 3, 4, and 5. So you see that as we increase the number of planes, these domes come closer and eventually superimpose. So if we look at our expression for these 2 points here, you see that x minus, for example, is x0 plus or minus this. And this eta of g is Gn is a monotonically increasing function of n. So it's easy to understand from here why we have observe that the center remains, but the dome becomes wider. So this can be easily explained by this equation. So these are basically our results. So in conclusion, we have obtained an analytic expressions for Tc of x for the superconducting dome, which is excellent in comparison to the single-layered cuprates. For the multi-layered cuprates, we will have the same problem here because we are not going to dope homogeneously. Then we have a very simple explanation for the increase of Tc optimal as a function of the number of layers. It's just an enhancement of the effective coupling as we introduce that. And then we have another, again, a very simple explanation for the superposition of the superconducting and antiferromagnetic domes as we increase n. A consequence of our results is that optimal doping corresponds to a vanishing chemical potential. Based on this analysis, we can suggest a way of increasing Tc. How can we increase Tc? Because it's of no use to increase the number of planes because we cannot dope them properly. So a suggestion to our material science colleagues is try to build a material such that the primitive unit self, contains another charge reservoir in here, in such a way that we intercalate no more than 2 copper oxide planes between the charge reservoirs. This will increase Tc. So how to do that is up to the material science colleagues. But for sure, if we can build a material with another charge reservoir here, we will certainly increase Tc. So there are many perspectives that come out of this. We are working on the pseudo gap, description of pseudo gap. Then we can study resistivity as a function of temperature in the non-superconducting phase. Pressure effects. These pressure effects, by the way, can be, if you look at the optimal, this eta, Okay, you see this delta is a function of the area of the primitive unit cell. So this area is certainly a function of the pressure. So if you apply pressure, this area will diminish, decrease. So it's very easy to study if pressure effects in this framework. So to conclude, we are not presenting a theory for high TC superconductivity, but whatever this theory might be, it must, at a certain level, coincide with the BCS-like theory we introduced here, because it's not by chance that it's reproducing so well the experiment. So this can give hints for what should be a definite theory for high DC superconductivity. Thank you. Let me just show. This is a paper with Marcelo where you obtained this antiferromagnetic dome. So this is the result of the present paper. So we are progressively covering the phase diagram. Okay. Okay. This we did in this paper. The basic idea is that as we introduce a hole in the oxygen lattice, we create a Skyrmion defect in the antiferromagnetic copper lattice. And as we dope, the energy of this defect progressively goes down to 0. And when it becomes 0, you are at the Néel temperature. So that's how we can obtain the magnetic dome. Okay. Well, I think muon relaxation. Yeah. There is a. I think this paper here. This paper here discusses that, because these figures are taken from this paper. But it's very intuitive. No. You see, this is LSO is n equals 1, but 2, 3, 4, and 5 are not LSO. No, LSO has just one layer. Yeah. If you look at this figure, it's quite intuitive. But, okay. Okay. Okay, I think this has been addressed in this paper. This paper here. I think they do muon relaxation experiment. Okay, then what would be the... Yeah, but disorder here mean the number of holes that you... So the number of holes increase. As you increase the number of holes, you increase TC. Okay, we are not including disorder in this. Just the fact of the oxygen holes. Yes. Yeah, but there is a distance. There is a distance. No, no, no. It's just a picture. No, no, no. The only thing we are okay, but we have in our calculation something very suggestive that for n equals 2, we hit the experiment. Our formula hits the experimental value. For n equals 3, is almost. For n equals 4 and 5, it's completely different. And the values are similar to n equals 2, which you see that n equals 4 and 5, there are only 2 layers which are close to the charge reservoir. So, okay, it's very... Okay. No, but okay, but this must tell something to you. No, it's a comparison between this expression and the experimental value. Well, I don't know, but okay, I'm not saying that. Okay, is there any other explanation for that in the literature? That's the thing. So if you can find a better explanation, tell me. Okay. Okay. Sure. Okay, that can be done. Sure. Okay, that's correct. But this depends on very tricky model to describe where the holes go. No, that's true. Okay. No, I agree. That's correct. But the indication here is that the result you obtain, assuming they are equally doped, it's exactly what you have for n equals 2, and quite different for n equals 4 and 5. Well, I think it's difficult to do it from first principles. But of course, you can do some phenomenological description. Yeah, you can put different Lagrange multipliers for each one. That's correct. Yeah, it can be done. Okay, I'm not describing this quantitatively. The reason is uh, for multi-layered, again, we would have to do this that we are talking, because we are assuming evenly doped layers. So, but it's just a qualitative explanation. So from this, we see that these points we obtain increase with n. So it's a qualitatively description here. So what you say, it's true. Another reason is why these are not necessarily, these are not compounds of the same family, you see. So it's, you cannot do quantitatively description. But qualitatively, it's quite clear what's happening. Thanks.